I'd like to show you something rather remarkable, an oscillator so efficient that it'll work on less than a volt and practically no current at all, just from a wet finger and these two electrodes. Here is the secret, a transistor. Let us examine one. Very small to look at, but inside minute. Just 3 connections to a very small piece of special material, germanium. Germanium and silicon are becoming of tremendous importance to us. Through devices made from them, we may power electric locomotives or pocket radio sets. They aid medical research and researches into space. We can switch on machines in steelworks or subscribers in telephone exchanges. The super efficiency and wide variety of their applications makes them almost revolutionary. They are called semiconductors. We all know the conductors. Here is one, a rod of copper. We know the non-conductors, the insulators. Glass is an insulator. This simple conductivity meter shows us how well copper conducts electricity, and how well glass will completely prevent its flow. Since an electric current is the movement of charges in a field of force, copper must have an abundant supply of available charges, while glass can have none. Current moves to work for us through the conductors. The insulators keep it in its place and prevent dangerous and wasteful leakage. From conductors and insulators and just a few other materials are designed and manufactured all the electrical things we know. Let's see now what a semiconductor does. Here is one, a rod of silicon. It appears to be just what its name suggests, something with more charges available than an insulator, but less than a conductor. A half and half kind of electrical material. If it were only just that, it would have remained virtually useless to electrical technology. But a big research effort into how it works as it does has enabled us to turn semiconduction to our great advantage by understanding charge availability, how to control it, and how to use it. This second rod of silicon, by appearances, is identical with this, but it is a much better conductor. Both are exceptionally pure silicon, but the better conductor contains the merest trace, 1 part in a million, of phosphorus. This third rod also contains the merest trace of impurity, in this case aluminium. It is also a better conductor. So we can increase charge availability by impurities. But that is not all. Let's heat these rods. We put them into identical circuits, each joined directly to its own microammeter. Now we heat first the end of the bar containing the aluminium impurity. Current flows through the meter and the needle moves. Now let us heat the corresponding end of the phosphorus impurity bar. Again current flows and the needle moves, but in the opposite direction. Both circuits are arranged in exactly the same manner and are in all respects identical, except for the merest trace of aluminium in this rod and the merest trace of phosphorus in this one. Now, electric charges are of 2 equal but opposite kinds, positive and negative. It looks as if heat is giving energy to negative charges in this rod and positive charges in this one. And the movement of these charges is producing a voltage across the rods, causing the currents through the microammeters to be opposite. A profound electrical effect through minute traces of chemicals. But how? We have to look right into the very structure of a semiconductor to see the way impurity atoms do this. Let us examine this piece of silicon. We cut a slice, polish it, and etch it, and look at it considerably magnified. We see that it is composed of a large number of small crystals. We increase the enlargement. Then, if with some special form of vision, we could peer right inside a single crystal, calling on stupendous powers of magnification, and imagining the silicon atoms as black balls, we should see them arranged in space with beautiful regularity, each atom joined to its neighbors by 4 equally spaced bonds. This is the space lattice of silicon and germanium. Of course, the atoms are not like black balls, nor are the bonds rigid as in this model. The bonds are binding forces of electricity formed by whirling electrons orbiting around the atomic nuclei. An atom consists of a nucleus heavy in comparison with the electrons that move around it. When atoms of silicon and germanium get together to form a solid, these electrons get shared between adjacent atoms, forming bonds known as double bonds, because each is the linkage of 2 electrons, thus building up a lattice-like structure of atoms. Here we show one plane of the lattice. The bonds are widened and colored an intense blue to suggest their electric nature, shimmering to suggest their restless movement. We have colored the atoms green. Let this indicate the neutrality that is indeed their electrical state, for the silicon is cold. It is absolutely pure, it is mechanically perfect, and it is in no electric field. No charges move except in their natural orbits, and every negative charge is balanced by the positive charges of the nucleus. Now let us take out one of the silicon atoms and thus remove also the electrons which make up half of the double bonds that hold it. And replace it with an atom of aluminium. This element, however, is trivalent. Its 3 outermost or valence electrons share orbits with electrons from the neighboring silicon atoms, and thus we make 3 of the double bonds, but not the 4th. Where there have been 2 electrons in joint orbit, now there is but 1. There is an absence of an electron. The semiconductor technologists call it a hole, and we represent it here by whiteness. Nature, when building silicon atoms into solid silicon, would have had an electron here, a negative charge. We, by inserting a foreign atom, create the absence of a negative charge, thus, in effect, creating a positive one. So we have learnt how to make in silicon positive charges available. Now take another piece of silicon. Again remove one atom, but this time in its place insert an atom of a pentavalent element, for example phosphorus. Now we have a situation in which not only are the 4 double bonds remade, but we have a valence electron left over, a spare negative charge. Thus we learn how to make negative charges available. That material which has negative charge availability is called N-type. That with positive charge availability is called P-type. These, then, are the basic materials from which are made all the devices of the semiconductor family. Let's take as an example one that is considerably simpler in principle than a transistor, but of great industrial importance, a semiconductor power rectifier. This rod of silicon, one large single crystal, is doped with phosphorus to make it N-type. We will cut a slice from it, taking one of these, and although this is only a semiconductor, it is very thin and it will conduct current quite well. This is a reversing switch, and note that the slice conducts equally well in either direction of the current. Now we will change this N-type slice for part of its depth to P-type by introducing into it some trivalent atoms such as aluminium. We place on the slice a piece of aluminium foil and put it on the belt going into the furnace. Now what will happen is this. Imagine this to be our slice of N-type silicon and this our aluminium. The aluminium will first melt, alloy with the silicon, and then by diffusing in, cancel, so to speak, the N-type properties and change it over to P-type. We time the travel through the furnace at just the right speed so that when the slice emerges, we have within it P-type material joined to N-type, like that. Now if we place the slice in circuit, it conducts just as it did before one way of the current, but on reversing the voltage, practically no current flows. We have made a rectifier. What a remarkable change to have brought about by forming a PN junction inside the slice. How does it rectify? We will build up a junction in diagram form.